Hello, welcome back to the playlist of lectures on correlation, simple and multiple linear regression models. I am Hemakumar Kasala, and in the second lecture in the series, we focus on the topic of least squares line and regression. Given a linear correlation exists between variables in a bivariate data set, we explore if there exists a possibility to predict the dependent variable y for a selected value of the independent variable x. Arriving at a best fit line, the least squares line, to carry out such a prediction. Understand the relationship between the correlation coefficient r and the slope of the least squares line. Understand the concept of regression. Apply the least squares line or the regression line to predict the dependent variable y and understand its limitations. Let's get into the lecture. As part of the previous lecture on correlation, we learned how to quantify the linear relationship, if any, in a bivariate dataset x and y. We understood methods which quantify the linear relationship via the Pearson's sample correlation coefficient, along with the sign plus or minus, which qualifies the direction in the relationship, that is, x or y increasing or decreasing together or changing in opposite directions with respect to each other. In this lecture, we will learn if one of the bivariate variables can be predicted given a value for the other variable when there exists a linear relationship between them. We discussed about a virtual line and the deviations of the data points in the scatter plot about this line decide the correlation coefficient r. Such a line that is best fitted amongst the data in the sample can serve to predict value in y for a chosen value of x, not part of the data set in the sample, though not outside the range of x in the sample data set. Variable y is often referred as the dependent or response variable, and variable x is called as the independent predictor or explanatory variable. The general form of a linear relationship between x and y is given by y hat equals a plus b multiplied by x star, where y hat is the predicted value of y for a selected value of x that equals x star, and b equals the slope of the line, and a, called as the intercept, equals the value of y when x equals 0. For every change of 1 unit in x, change in y equals plus b when the slope is positive, and it equals minus b when the slope is negative. The straight line happens to be the best fit for the sample data set when a function of the vertical distances, that is deviations from the straight line, is minimum. The vertical distances, that is deviations from the straight line, equals y minus y hat, where y equals the actual value of y at each bivariate data point xy in the sample. Y hat equals predicted value of y for every x in the sample, which equals, as discussed, a plus or minus b multiplied by x, where b here just represents the magnitude part of the slope alone. The function of the deviations that is used to arrive at the straight line that offers the best fit within the sample data is given by sigma y minus a plus or minus b multiplied by x the whole square, which is the sum of the squares of the errors, in other words the deviations, that when expanded equals y1 minus a plus or minus b multiplied by x1 the whole square plus y2 minus a plus or minus b multiplied by x2 the whole square, and so on until yn minus a plus or minus b multiplied by xn the whole square. The values a and b for the best fit line are arrived such that the sum of the squares of the errors is the least, that is sigma y minus a plus or minus b multiplied by x the whole square is the lowest value. Such a line is called as the least squares line, also called as the sample regression line. The values for the slope b and the intercept a that constitute the least squares line can be derived as slope of the least squares line b equals sigma x minus x bar multiplied by y minus y bar divided by sigma x minus x bar the whole square, where y bar and x bar are the mean values of y and x data in the sample respectively. And the y-intercept a equals y bar minus b multiplied by x bar. The equation for the least squares line is y hat equals a plus or minus b multiplied by x, where y hat is the predicted value for y resulting from the substitution of a particular value for x in the least squares line equation. Notice that the expression to arrive at a, that is a equals y bar minus b multiplied by x bar, hints that the least squares line passes through a point whose coordinates are the mean values of x and y, that is x bar and y bar respectively. Let's understand the least squares line fit with an example. A sample of 10 different weightlifters who return to active sports after an arthroscopic surgery is chosen, and their time taken to return to sport after the surgery, which is the y variable, versus their age, which is the x variable, is listed here. Scatter plot for x and y are plotted below. Scatter plot for x and y shows a roughly linear relationship, and a least squares line that can be fitted into this data is constructed. The intercept and the slope coefficients are calculated as a equals minus 5.05 and b equals 0.27. The equation for the least squares line thus constructed is y hat equals minus 5.05 plus 0.27 multiplied by x. This equation y hat equals minus 5.05 plus 0.27 multiplied by x can be used to predict the value for y, that is the return time to sport, for a chosen value of x within the range 26 to 34. We'll discuss on the restriction particularly on the range of the x values soon, so hold on till then. For example, choosing a value for age as x equals 29, we can predict y hat equals minus 5.05 plus 0.27 multiplied by 29, which equals 2.78, that approximates to 3 days. Therefore, we predict that a person of age 29 undergoing an arthroscopic surgery is expected to return to sport after a gap of 3 days roughly. Remember, we arrived at this least squares line or the sample regression line by continuing the discussion on the correlation coefficient, and the deviations of the data points about a virtual line influence the value of the correlation coefficient R. Let's proceed to examine if the y-intercept A and the slope of the least squares line B bears any relation with the correlation coefficient R. In order to arrive at the relationship between B and R, let's start doing some manipulations to the equation for B. To start with, let's divide the numerator and denominator with the product of the sample standard deviations of x and y, which are Sx and Sy respectively. Note, since we do not know the population standard deviations sigma x and sigma y, we use the respective sample standard deviations instead. Therefore, B equals sigma x minus x bar multiplied by y minus y bar divided by the product of Sx and Sy divided by sigma x minus x bar the whole square divided by the product of Sx and Sy. Since x minus x bar divided by Sx equals Zx and y minus y bar divided by Sy equals Zy, the expression for B can be written as sigma Zx multiplied by Zy divided by sigma x minus x bar the whole square multiplied by the product of Sx and Sy. Now let's divide the numerator and denominator with n minus 1, that is the sample size minus 1. Since sigma zx multiplied by zy divided by n minus 1 is nothing but r, and sigma x minus x bar the whole square divided by n minus 1 is nothing but sx square, the expression for b becomes r divided by sx square multiplied by the product of sx multiplied by sy. Cancelling the sx in the denominator and the numerator, b can be rewritten as b equals r multiplied by sy divided by sx. Therefore, the slope of the least squares, that is the sample regression line, b equals the correlation coefficient r multiplied by the ratio of the sample standard deviation of y to the sample standard deviation of x. b equals r multiplied by sy divided by sx implies slope of the regression line is decided by the extent of the correlation r and the ratio of the sample standard deviations of y and x. Magnitude of b is a fraction of sy divided by sx, where b is maximum and equal to sy divided by sx when r equals plus or minus 1, and a fraction of sy divided by sx as magnitude of r reduces. Where x and y are perfectly correlated, that is r equals 1, the magnitude of the slope of the regression line equals the ratio of the sample standard deviations of y and x, whereas magnitude of the slope reduces as r reduces from 1 for a given ratio of sy to sx. Sign of b is decided by the sign of the correlation coefficient r. b is positive when r is positive and b is negative when r is negative. Substituting for a, that is a equals y bar minus b multiplied by x bar in the expression for y hat, that is y hat equals a plus r multiplied by sy divided by sx multiplied by x, we arrive at y hat equals y bar plus r multiplied by sy divided by sx multiplied by x minus x bar. Suppose we consider a change in x such that x minus x bar equals sx, that is one sample standard deviation in x. Y hat equals y bar plus r multiplied by sy divided by sx multiplied by sx. Cancelling the sx in the numerator and the denominator, we get y hat equals y bar plus r multiplied by sy. Please note that r in the above expressions can either be positive or negative. Y hat equals y bar plus r multiplied by sy implies for a change in x value equal to one standard deviation, that is sx, the change in the predicted value y hat equals r multiplied by sy, that is r times the standard deviation of y. Unless r equals 1, which is rare, the change in the predicted value y hat is relatively less compared to the change in x. That is, for one unit change in x, that is sx, the change in y is only a fraction of sy. Lesser the value of r is, much lesser is the change in the predicted value y hat with respect to its mean y bar. That suggests that there is a tendency in the predicted value y hat to get pulled back or regress towards the mean y bar along the least squares line even when the change in the independent variable x is large. That is the reason the least squares line is also called as the sample regression line. Cautions on using the least squares or the regression line. The regression line is used to predict the dependent or the response variable y for a selected value of an independent or predictor or explanatory variable x. The regression line should not be used to predict the independent variable x for a selected value of the dependent variable y. The simple reason being the regression line is arrived at by minimizing the vertical distances of y values, not the x values, with respect to that line. Also, never attempt to predict the dependent variable using a value of x that is well outside the range of the values in the sample data. The fit and the linearity of the regression line is not guaranteed outside this range. That brings us to the end of the lecture on least squares line and regression, which is the second lecture in the playlist of lectures on correlation, simple and multiple linear regression models. See you soon back with the next lecture in the series. Bye until then.